Ubuntu. Oh, wait. Oh, you. Oh, it's just Ubuntu.
Yeah,
That's
good.
good. No, you scrubbed it.
It came pre-installed.
All right, so
Why, yeah.
today we are finishing also our series dedicated to 3D nuclear structure. Giuseppe Bozzi from University of Cagliari give us to talk about technology of unpolarized TMDs. Floor is yours. Thank you.
So, good morning, everyone. We already met in the corridor somewhere because I'm here since last Sunday. So you probably already have exchanged a little word with me. But nonetheless, I will introduce myself. I'm working at the University of Cagliari. I'm a theorist. I'm, let's say, interested. I became interested in this wonderful field, so TMD PDFs and hadron structure, because it is the main concern, if you want, for precision physics. I always did precision physics at the LHC. So I did precision predictions for electroweak observables at the LHC, for instance. And since in the last 20 years, there has been an enormous progress in the field of perturbative QCD. And so predictions are now known also to N3LO or beyond accuracy. Now the frontier of precision physics is having under control this kind of effects, the effects coming from the hadron structure. So a good knowledge of the proton structures, or the proton structure in particular for unpolarized TMD-PDF, because it's what collide at the LHC and at the hadron colliders, is essential to attain the precision needed for the electroweak tests of the standard model. Okay. So today I will try to give you an overview of the recent activities that have been devoted to the terminology of unpolarized TMDs, and this will complete the series of lectures on hadron structure that Alexei began last week with the first two lectures. And actually, he did quite a good work in saving me time from explaining the TMD formula, but nonetheless, I will give an overview again of what he already explained and then move on. So let's start from the very basic stuff. I will just give you a brief overview of TMD PDFs. You always start with the collinear PDF, of course, or collinear computation functions, which only depend on one variable, which is the longitudinal momentum fraction, other than, of course, the scale at which you consider them. And this kind of PDF has reached a high level of accuracy. This is just a random figure, a random plot that I downloaded. It's relative to the NNPDF 3.1 computed and next to leading order, and you recognize the basic ingredients of your collinear PDF. So the balance work, which amounts to 2/3 of the content of the proton for the up and 1/3 for the down at very large at quite large values of x, and then you have the explosion of other flavors at smaller x, where you have splitting going on. In particular, the gluon will be extremely relevant, of course, at small x, as you probably already know. So let's move to the TMD PDFs, which depend on an additional variable, which is the intrinsic transverse momentum, and offer you a three-dimensional imaging of the proton. And you can get plots like this one, where you plot at different values of the longitudinal momentum fraction, the TMD PDF in kx and ky, which are the intrinsic transverse momentum on the two transverse axes x and y. In this lecture, I will focus only on unpolarized quark TMDs. But this is, of course, just a subset of the total panorama of TMDs that one could explore. The processes for which TMD factorization has been proven, and you can find all kind of factorization theorem, factorization proofs in Collins' book, for instance, in the recent, now it's 10 years ago, I guess, the famous Collins book. And these three processes are Drellian process, where you produce a lepton pair from a proton-proton or proton-antiproton collision. In this case, you have two TMD PDFs from the initial state here, these two blobs here and here, and you have lots of data available for this process, coming from low energy, low Q squared data from Fermilab, for instance, mid energy data from RIC, and high energy data both from Tevatron and the LHC. The second process for which TND factorization has been proven is the semi-inclusive DIS, where you have the production of a hadron in the final state with a target hadron in the final state with some transverse momentum coming from the deep inelastic scattering of a lepton over a proton target. And you have one TMD PDF in this case and one fragmentation functions as well. We have many, many precise data points for this process coming mainly from two experiments, Hermes at AZ and Compass at CERN. And this will provide, let's say, the bulk of a fit to TMD PDFs, as you will see in a moment. Then we have E plus E minus annihilation, which is the third process of which TMD factorization has been proven. And you have two TMD fragmentation functions in the final state. You basically produce two hadrons from an annihilation of a pair of leptons. This could be provided by two experiments, Bell at Keck and Babar at SLAC, but unfortunately, these data are still missing. So we cannot properly compare theoretical predictions with this data. There are discussions going on with experimentalists on the possibility of having precision data for this process, which would help a lot in disentangling the TMD fragmentation function from the TMD PDF. But up to now, no results have been published that can be used for fit of TMD PDFs and TMDFS. Sorry. So let's go a little bit into details, starting from Drellian. This is the formula that you probably have already seen many times, and this is the differential cross-section, which is expressed in terms of two TMD PDFs, depending on the longitudinal momentum fraction, the K-perp, the renormalization group scale and the rapidity scale, mu and zeta A and zeta B. You have a hard coefficient functions in front, which contains all the process dependence of this formula, while the second part is supposed to be universal because it contains everything that has to be assigned to TMD PDFs. Okay. In the direct space, in the K per space, you have this delta, which guarantees the conservation of the conservation of transverse momentum. So K per A plus K per B must be equal to QT. And as you probably have already seen from Alexei's lecture, it is customary to rephrase this formula in B space, where this delta gives rise to complex exponential that allows you to convert this two TMD PDFs expressed in K-perp space to TMD PDFs expressed in BT space. Okay, and so this is the custom way in which factorization formula for Drellian is usually expressed. Okay, so I have the appearance of a Bessel function here, and the direct product of these two TMD PDFs. The same can be written also, of course, for semi-inclusive DIS, which is this process here. You have one quark TMD fragmentation function, one quark TMD proton distribution, parton distribution functions. This is the delta containing the conservation of the transverse momentum. And these are the TMD PDF and TMD FF. The structure is exactly the same as before. This is still the hard coefficient function that contains the process dependence of your formula, and this is universal. You can again go to the impact parameter space and write this as a direct product of the two ND PDFs and FF in this space. Just a little remark on kinematics. This delta function is strictly valid only if you are in the so-called TMD factorization region. So when Qt is much less than Q. If this is true, then this, which will be the right expression for Qt mu as a function of the other quantities in this diagram, reduces to this simple formula here. Okay? Otherwise, you have to take into account this complete formula. But in order to be sure that we are in the right region where TMD factorization apply, this equivalence reduces to this one, and you can write this kind of conservation. Okay. Then, of course, if we would have this kind of process, this kind of data available, we could write this analogous formula for TMD factorization, where again the two TMD fragmentation functions can be expressed in this space and then expressed as a simple product. Okay. This is quite analogous to the Drellian case, where you have the two final transverse momenta rescaled by the Z1 and Z2 variable, which have to be equal to the Qt, where Qt is the transverse momentum of the fold. Basically, the mirror of the dy process. Okay. Okay. This is the TMD structure. I guess Alexei already showed you this formula. Now we will go a little bit in detail into each one of these elements and see what has to be determined from fitting to real data. Okay. So, but before doing so, let me just offer you a different perspective on how you can arrive at this formula, at this final formula for TMDs. I will give you a different perspective by providing a brief sketch on how the resummation of double logs and single logs works, starting from a heuristic point of view, from a purely diagram point of view. Then make some connections with the TMD form. So let's focus on the dy process, which is this one. Okay, on a very simple process. Okay, and suppose you have the emission of a gluon from initial state. This one. This is P, this is K, the full momentum of the gluon, and this is P minus K. So as soon as you allow first soft emission from the initial state, you have the appearance of this propagator, right? So you have something that scales like 1 P minus K squared. Okay, 1 over P minus K squared is, if everything is massless, it's basically equal to this. Okay, and this is basically equal to 1 over the energy of the gluon times 1 over A cos theta, where cos theta is the angle between P and K, right? So more or less, this is the sketch. So you quite clearly see where the problem comes from. The problems come from the gluon being too soft, so first divergence, soft divergence, or the gluon being too collinear, quark, second divergence. So you can have three possibilities. Either the gluon is only soft, either the gluon is only collinear, or the gluon is soft and collinear. So you will have, in the worst case situation, you have the gluon being both soft and collinear, and you will have alpha S log squared. Okay. If the gluon is only soft or only collinear, you will have alpha S log. In all other cases, you have no divergences. Okay, so you have finite terms here. And this is the order alpha S correction to your Drellian process. Now imagine going for a second emission. Then you have two gluons. They can be both soft and collinear, and then you have alpha s squared log to the fourth. Or you can have one soft and collinear and the other only soft or only collinear. So you have alpha 2s log cube, and then go on. Okay? This is the order alpha s squared correction. Well, I don't need to convince you that this table can be can go on forever. Okay, so in general, you will have alpha s to the n log to n, alpha s to the n log to n minus 1, and so on. So if you rely on pure perturbation theory, in selected region of the phase space, which are the ones we are interested in, perturbation theory fails dramatically because these quantities diverge in these regions of the phase space. So what you would prefer to do is trying to make sense of each column of this table instead of looking at rows of this table. If you're able to sum all this contribution from the first column, so all the leading logs, then you're okay because you have a leading log formula if you are able to do it. Then you have a next to leading log formula from this column, a next to leading log formula from this column, and so on. Okay. So the question is, are we sure we are able to sum all these columns in this table? Yeah, the answer is yes. The answer has been provided many years ago in the 80s and also in the following years by Collins, Obersterman, and other collaborators and other contributions from other sides as well. And this formula can be expressed in an alternative way other than this one, in this way. You have L first function, which is usually called G1, which resums the leading log. Your second formula, resumming the next to leading log. A third formula, resumming next to leading log, and so on. Okay? So, as you can see, this formula, which are basically equivalent, this expression here, I will show you in a moment. This expansion is very well behaved compared to the previous expansion in terms of rows. Why? Because if you look at how much are suppressed relative terms of this expansion one respect to the other, these are suppressed by 1 power of alpha s. Okay, so consider alpha s log as a single item. If I put an L here, this means that this expression is suppressed by this one by order alpha s. This expression is suppressed by this one by an order alpha s. With respect to this one by an order alpha s. Okay, so this is a converging expansion in the problematic region of the phase space, contrary to the Ross expansion, which is diverging. Okay. So when you are confined in the region where you have large logs, it is much more desirable to have this at hand, so this formula at hand, by columns, instead of this. Of course, you have to be careful, because if you simply sum the result coming from the different columns and the result coming from the rows, because you want to have a full prediction of the entire spectrum, not only in the regions where you need reservation, then you have to avoid double count. And so you have to reliably match the two procedures. But this, I will discuss it at the end of the lecture. Okay? So for the moment, let's assume that we know how to perform this sum. Okay? And we know how to exchange a diverging expansion with a converging expansion. Okay? So this first row of the TMD formula is the so-called matching to the collinear PDF at very small bt. Very small bt, since bt is the Fourier transform of qt, means large qt. Okay, so we are in the perturbative region. Okay, and so you see that here you have the collinear, you have the collinear PDF, which is somehow corrected by a coefficient functions that provides this kind of matching. So provides the fact that your TMDs is effectively reduced in the large Qt region to the collinear PDF as it should. Okay? This set of coefficient functions can be obtained basically in two ways. Either you expand your resummation formula here, your TMD evolution formula, and you compare it to each of these terms at different level of perturbative fixed order, and then you get this coefficient because eventually you want to reproduce this result at large Qt, right? The one we've written here. So either you do a direct comparison of the expansion of the evolution formula with this expansion, or you take your matrix element definition. For instance, you can find it from in chapter 3, I guess, of the TME handbook, and you perform this this matching directly with the matrix operator definition. So the two procedures have to give you the same answer. Usually, this is the most practical one, let's say, since these calculations are known since many years. And so if you expand your formula and match the coefficients, then you're basically done. But you're free to work with matrix element operators as well. So the first law is as a perturbative origin and provides the matching to the collinear PDF. The second law is what is the proper evolution of your TMDs, and it's composed of two pieces: the Collins-Soper evolution and the renormalization group evolution to large PT, which is the region where you want resummation or TMD factorization to be effective, because large PT is small Qt. Okay, it has a perturbative origin as well, and I mean, it is expressed in terms of perturbative functions. This one has a perturbative expansion. This one is a perturbative expansion. This one is a perturbative expansion as well. Okay, so they can be computed order by order in alpha S. And we'll start, of course, at order alpha S. They do not have a constant terms. They start at order alpha S because they are basically given by this kind of mission. Okay? So their origin can be traced back to this kind of process, and so they need an alpha S to be generated. Okay. This is in contrast to what happens to this coefficient function, which is different from zero also at alpha S equals 0, because you need to match at collinear PDFs also at the very lowest order. Okay? And I forgot to say that this is not only different from 0 at the lowest order, but it's also a matrix in flavor, because when you emit a gluon here, or when you in QCT you evolve a parton, this parton can change flavor. So this coefficient function can, of course, depend on the flavor as well. And so it's a matrix rather than a simple function. Okay. For instance, the first coefficient, the first expression of this C function will be a delta ij delta 1 minus x. This is the very first term of the C coefficients. Then you have order alpha S. Okay, but this tells you that C is a matrix. Okay. Okay. This expression can be exactly matched in a univoc way to this expression here. Okay. So each of these functions can be expressed in terms of Collins-Soper kernels gamma F and gamma K. Okay. Because they have exactly the same origin. And this is also something that is mentioned in the TMD handbook in chapter 4, basically. There there is a long discussion on the difference and analogies between QT resummation and TMD factorization and evolution at TMD handbook. So please have a look, and of course we can talk about this during discussion. Given the fact that each of these functions have a perturbative expansion, then you can define a perturbative accuracy for your TMD formula. So you take the different elements, you combine them in a sensible way. This is a critical word, in a sensible way, and then you can define a perturbative accuracy for your TMD formula. So starting from the very first row, the leading log is simply given by H and C at the lowest order, because remember that they are different from zero also at the lowest order, as I said, and also the H function is different from zero as the lowest order. You cannot have K and gamma F, but you can have gamma K at the first order, because it will be of the same order, the same perturbative order of order zero in H and C. Normally, this is called leading log, okay? The next leading log has still H and C at order zero, but one order up in K and gamma F and gamma K. So the first order in K and gamma F and second order in gamma K. The reason why there is this so-called mismatch between gamma F and gamma K is this log here, okay? You see that this integral will give you a double log for gamma K and a single log for gamma F. Okay? And this is why you need one order higher in gamma K to have the same order in gamma F. Okay? Next to linear log will have 1, 2, 3, and next to linear order PDFs, and 3LL will have 2, 3, 4, and next to linear order PDF. So there is a different prescription, different accuracy that has been used in the past, which is this one, which is the NLL prime and NNLL prime. What is the difference? If you see the difference between NLL and NLL prime relies only in H and C and PDF and alpha S evolution, leading order and next to order, because K and gamma F and gamma K are exactly the same. So why these two accuracies can be, how can they be compared? Well, they can be compared in this way. If you look at the next leading log, the next leading log has a C0 coefficient, so with no alpha S, multiplied by these two expressions, the leading log and the next leading log contributions. Okay. Now, if you imagine to include the higher order term in next to the log. So if you imagine to include alpha S C1 here, this alpha S in the expanded formula will multiply this term and will give rise to alpha S n plus 1 log 2n. But alpha S n plus 1 log 2n is a next to the log contribution. The reason is very simple. Alpha S n plus 1, the leading log of this guy would be L2n plus 2, right? But if I have alpha S to the n log to 2n, this means that I go down by 2 powers with respect to the highest power. So it's a next to leading log contribution. And so these two accuracy, NLL and NLL prime, and the same can be said about this one and this one, are formally of the same logarithmic accuracy. And so you might ask, so why should we deal with this difference? Well, this difference is relevant once you want to make predictions on the whole QT spectrum. Because if you rely only on the first part of the QT spectrum, which is the low QT spectrum where TMD is in place, then you can use whichever you want. But if you want to take your predictions for PTZ, for instance, over the entire QT spectrum, then you need resummation at low QT, and you need fixed order at high QT. And fixed order contains this kind of contribution. And so in order to properly match the two, TMD evolution and the IQT tail, perturbative tail, you need to rely on primed counting. Otherwise, the two procedures don't match, let's say. You cannot perform a sensible match. I will discuss it a little bit later also this. But as far as the TM region is concerned, they are same logarithmic accuracy. So you can do basically what you want. You can choose basically what you want. Okay. Now we have the third row, but before going to the third row, I want to just highlight the fact that instead of the B, we have put B star here. And you have already seen what the B star is. It's a prescription to avoid the Landau pole, because eventually your quantities, especially alpha S, will be calculated in terms of B star. And so you have to guarantee that alpha S never crosses the Landau pole. And so you introduce a regularization, which basically prevents you from hitting this pole here for large B values. And normally, you can choose whatever prescription you want. There is no a formal prescription that you have to rely on. And this is one possible choice that we used in our fit, for instance, but it's just one of many. The only interesting thing is that the transition, the only interesting thing is that this B star is as close as possible to B for a large fraction of its life, let's say, in order not to modify a lot your integration, okay? And then it quickly saturates to the upper value, B max. So this function guarantees this kind of behavior, but you're free to choose whatever functions you want, okay? As long as... we also introduced this B-min, which is not strictly necessary. A B-min prescription is to forbid the TMD evolution to act also on in B region where it shouldn't act, because small b means large QT. At large QT, you have to switch off your resummation. So you don't want resummation effects to propagate also in this region. And so sometimes you can also introduce a BB prescription, but this is not compulsory as well. You can also introduce other prescription to avoid the introduction of this BB. The last item of this formula, which is this one, is the non-perturbative pure form factor, let's say, that parameterizes the transfer spot. And this is not given a priori. So you have to choose a functional form and fit this functional form to experimental data. So first row and second row are completely fixed by perturbative QCD. Perturbative expansion, pure perturbative accuracy. These are really written in stone. Let's say, okay. The only thing that you have to determine is this third row, non-perturbative form factor. And it may be possible that the non-perturbative form factor will eventually be determined in some way from lattice QCD. Because lattice QCD is rapidly advancing in the field. So probably at some point they will be able to provide an estimate also for this third row, which is purely non-perturbative. But for the moment, we have to rely to fit to experimental data. Okay. Questions up to now? Because the difficult hard part was this one. So if you followed me or heavy questions? No? You can see the non-perturbative form factor also in this way. This is also taken from the TMD handbook. So your real TMD is expressed in terms of a TMD computed at B star, so with the regularization prescription on. And then you have to account for the fact that you introduce this regularization. So you effectively cutting off your integral. Okay. And so the price of cutting off this integral is introducing the non-perturbative form factor. Okay. This is another way to see the introduction of the intrinsic KT. Okay. So the non-perturbative factor is unavoidable and it's intrinsically tied to the regularization procedure. If I change the choice of B star, this will reflect in a change of the non-perturbative factor. I hope this is clear. So it's kind of misleading to speak of a universal form factor. It is not a universal form factor. Your form factor will depend on the exact choice or your prescription and of course on the collinear PDF that you use as input. For each collinear PDF, you will have a different non-perturbative form factor. For each choice of B star, you have a different non-perturbative form factor. So no questions up to now? Because now it's the hands-on stuff, let's say, we will have dirty hands by digging into data. Okay. So just a disclaimer, I will talk about the extraction of TM-PDFs and FSS from low PT data. And since I'm actively involved in this kind of exercise, I will be maybe a little biased in the choice of what I will show. But this does not mean in any possible way that I claim that what we are doing as a group is the good way to do it, is the best way to do it, and it's the only way to do it. So please acknowledge the fact that I'm just showing results, which I am quite sure about how we did it and how and the choices that we have made. But there are many other groups performing fits that are doing their choice and their possible way of doing things. And I'm not claiming in any way that what I show is the truth. For instance, there's Tommaso here doing PDF fit, TMD fits. Sara as well is involved, I guess, in Madrid group in some way. I mean, there are a lot of good people doing the same exercise. So disclaimer, I'm not claiming I know the truth. Okay. So before going into details of the PDF fitting, TMD fitting, I'm just showing an overview of what are the available data sets. As far as Drelian is concerned, you have a grand total of 484 points. Why this particular number? Well, you have to make sure that you are in the TMD region, as I already said. And the TMD region is customarily considered to be this region here. The region where QT over Q, where Q is the invariant mass of the object you produce, so the invariant mass of the lepton pair, is less than 0.2. Okay? If we are in this region, we consider to be safe. Okay, but of course you can make variations of this number and see what happens to your fit. And I will show you in a moment we can do this exercise. So this line is square root of S collision. So first you have the low energy Fermilab experiments. 19.4, 23.8, 23.4, 38.8 is the square root of S of these three experiment, E605, E772, and E288. And they have a lot of numbers. So in total, they have 130 points, 130 beats for E288, and more than 100 for these two experiments. Then you have a few points at mid-energy. There are very, very few, less than 10 points from star and Phoenix combined. And then you have the high energy colliders, CDF and D0 from Tevatron at 1.80 eV and 1.96 eV, which amounts to a total of 70 points. And very high energy data from Atlas, CMS, and LHCb, which are really also very precise. This triggers some problems in fit procedure because too much precision, of course, is a challenge for your fitting capabilities. Okay. This is the entire data set that I put here for reference, but I will not go on describing all these experiments. I will just remark that some observables are purely differential, others are normalized. So you have to take into account also the normalization here when you perform your comparison with the theoretical predictions. I will just point out that LHC data are very, very detailed in rapidity. And this is crucial for a good extraction of PID fits, because the fact that they are pinned in rapidity allows you to constrain better the X dependence of your TMD PDFs. Okay, because inclusive inclusive data or data at fixed XF or fixed Y do not give you a lot of information on the X dependence, or better, they give you information only for some X dependence, on the whole X dependence of your TMDs. These are the lepton cuts that each experiments impose on their data. I will not give you details about how we implement, or in general in PDF fitting is implemented lepton cuts because it's a very long and difficult subject and will take more than 1 hour. So we'll skip this discussion. Series data, as I told you, Hermes and Compass provide lots of pins available. They are basically contained in the very narrow square root of S region, from 1 to 4 for Hermes and for 1 to 15 for Compass. And as I said, there are a lot of data, 1,547 passing these cuts. Now, this is a matter of discussion as well. As far as Drellian is concerned, we have a really simple recipe, QT over Q less than 0.2. Translating this into a cut selection for series data is not easy, because you have to, first you have to guarantee that you are inside the collinear factorization region. And so you have to impose these selection cuts, because Q less than the electron mass would, of course, take you out the collinear factorization. Then you have to also exclude some Z values of your data, because otherwise you will go into exclusive processes that we are not able to describe within TMD factorization. And so you have to exclude this high Z and low Z region. And then you have to cook up formula that mimics this simple formula for Drellian. And this formula is just a suggestion. It's the one we use in our fit, but of course it's not written on the stone. But we have found that allowing a Z dependence to percolate in this formula saves you from excluding too many data, while at the same time be quite sure that you can apply factorization theorems for series as well. But this is a matter of debate if you want. So if you want, this is a suggestion to translate this very simple formula, but we can discuss, okay? But the message is you have to invent something to discriminate from all this beautiful data in the series data sets. This is the table for series data sets. I leave you for reference here. As you can see, we have pi or k's in the final state, pi plus, pi minus, k plus, k minus, in the case of Hermes, and this allows you to disentangle also contribution for different flavors of quark, as I will show you at the end of the lecture. This is the XQ squared coverage of your data. As you see, Hermes and Compass are here in the bottom right corner of the diagram, so at very high values of X and very low values of Q squared. Then you have Tevatron experiments that go slightly up, Fermilab experiments that go slightly up in Q squared. CDF and D0 and Atlas LHC and LHCb and CMS data cover the high Q squared region or over a wide X interval. So they are very effective in covering this high Q squared region. You may notice that there is a big white hole here. And that's the reason why we're building the electron-ion collider, because the electron-ion collider will populate all this region here. Okay? So up to now, we only have, let's say, this very limited range of XQ square data. When the EIC will be operating, we will be able to fit a large amount of data also from this region. Now, I will just give you a very brief overview of the treatment of experimental uncertainties during FIT, but really 1 minute, less than 1 minute, because last week you had Stefano Forte here that I'm sure will had given you lots of details on this. So as the Latin said, ubi maior minor cessat. So I'm clearly minor than Stefano Forte, so you have learned a lot from him. I will not delve into details. I will just recall that experimental uncertainties have a statistical origin and a systematic origin, and the systematics can be uncorrelated or correlated. They have to be treated in different ways. The correlated ones can be additive or multiplicative. You can see this very well in the data provided by the experiments. You can build the covariance matrix that you have to put inside the chi-square in this way, with the variance for the uncorrelated uncertainties and a more or less complicated formula for correlated uncertainties. And what is typically done to reduce this covariance matrix to a diagonal form is to rely on shifted predictions. So you take your theoretical predictions Ti and you shift it by an amount Di, which is dictated by nuisance parameters, lambda alpha, which are computed by minimization of your chi-square with respect to the same parameters. And then if you use this systematic shift, you can write a chi-squared, which is totally diagonal, at the price of a penalty term, which is given by the sum of your nuisance parameters. Okay, so this is really chi-square in a nutshell, but I invite you to read back the lecture of Stefano Forte to have more details. Okay. Now, TMD global fits. As I said, there are many fits around. I chose, for time reason and also for in order to make a selection of the many fits that I could show, only global fits. Global fits means that these extractions made use of the full data set that I showed you up to now. So both cities and NDY processes. But of course, you can also choose to fit only Drellian or only cities, and you can also choose to fit only low energy data or only high energy data. I mean, you can do any selection you want based on your personal convictions, of course. I had to make a selection, and my selection is based on what I was involved into, and so what I knows best, basically. Okay, so I repeat for the third time that I'm not claiming that these are the good guys and all the others are not. Okay. The very first global fit was this one from 2007 from the Pavia group at next to the log. So very limited theoretical accuracy, all data, 8,000 data in total, because they also relaxed it a little bit, the conditions on cities data. So the complicated formula we have seen before cuts away a lot of data. They decided to take a lot of data more from Hermes and Compass and reach this precision for the chi-squared. Then there is Madrid group who performed a global extraction in 2019 and NCLL minus. So why would you see that minus? Because if you remember the table, you have to strictly adhere to that prescriptions, okay? Each row has to be fulfilled entirely. At the moment they performed this fit, collinear fragmentation functions were not known at next to Lane order. And they used fragmentation functions at next to Lane order. This is a penalty term, let's say, that explains why you have a minus here. And you have also a minus here, because also the MAP22 extractions used the next to Lane order fragmentation function. So it has to be decreased a little bit in accuracy. You may think that I'm too strict, but actually in perturbative expansion, you have to be really strict, because otherwise you get your results get easily jeopardized. Okay, I will give you more details in a moment. And then there's a brand new extraction, which is not published yet, but it's on the archive, which is N3LL with next in order factorization function. So the true N3LL here, and it's also flavor dependent. A fit also depends on the number of parameters you have. This fit had 11 parameters. Also, this one had 11 parameters. This fit has 21 parameters. And this one is 20 parameters for the unflavored version and 96 for the flavor dependent set. Because, I mean, for each flavor, you have to add single parameters. Okay. The functional forms is entirely up to you. There is no prescription for a functional form. There are basic constraints. I mean, for instance, you want a TMD PDF to be positive definite. Okay, and so you usually choose Gaussian functions. Okay, this is the Gaussian function, and this is the Gaussian function as well. But other than that, you are basically free to choose whatever you like. There is an important quantity that is supposed, let's say, to be universal, which is the Collins superkernel, that, as you know, is composed by a purely perturbative part plus a non-perturbative part. And this is the key that allows you to compare very different fits. In other words, even though these two functional forms might be very, very different, the extraction of the Collins superkernel, that I will show you in a moment, might be reasonably the same for the two extractions, okay? Because this is supposed to be universal. Okay, so this is sensible comparison among different fits is given from the Collins superkernel. A typical plot that you can find in this fitting exercises is the comparison of the fitted curve that you obtain from the global fit to single plots from single experiments. For cities in particular, in the COMPAS data, you have this comparison performed by the Madrid group in 2019. Filled points are points that have been fitted. These other are points that have been discarded for the fit. So this plots allows you to judge the quality of the fit because, I mean, fitted points are, of course, reproduced more or less, okay? But then also not fitted points are quite reproduced as well. And this is an indication of the quality of the fit, if you want. How much can you trust your fitted parameters, okay? Offset here doesn't mean that you have a problem with normalization. Offset only means that they decided to shift these two curves in order to improve readability. Okay? This is not a true offset, a real offset. They just improve readability. This is what happens for Drellian data instead. You have low energy data that suffer from large experimental uncertainties, and this also reflects in some way into a poor determination of the fitting parameters. Okay, and so this is why you see an increase in the uncertainty band from the all the uncertainty that I show for the fit are 1 sigma 68% confidence level for the parameters that you obtain from the fit. Okay, so this is a 1 sigma of the parameters obtained in the fit. So E288 is large uncertainties. CDF is reasonably described, but I mean, the shape is quite, I mean, we are within errors, but the shape could be better. CMS is quite reasonably described. Of course, Atlas data, which are astonishingly precise, as you can see, give us the main problems. Because as you can see also from this ratio data over predictions, Atlas data have a very bad chi-square. And this is typical, okay? Because when you try to perform a global fit, the desire to keep together very low energy data with big uncertainties, and very high energy data with smaller uncertainties is really a difficult exercise. And things like this could happen also if your global chi-squared is very good. Okay, global chi-squared here is 1 point something, but this single chi-squared, I don't remember by heart the name, but it was more than 5. Okay, this can happen. Okay, it's a difficult exercise. The result of the fit is the TMD-PDF. Here I show you 3 different examples of TMD-PDFs. The Madrid group chose to plot PDF, TMD-PDF as a function of B. So you cannot directly compare with these other 2 plots, which are as a function of K-perp. But I mean, you can by remembering that B is the inverse of K-perp, maybe you can try to look at some comparison, but it's not easy. Okay. If you look at this plot, at this right plot here, you see that of course the TMD-PDFs are peaked at 0, and then they decrease as a Gaussian. With very large uncertainties for very low X, and this reflects the fact that we have poor data at low X. If we had more data at low X, this band would be narrow as this one and this one, which are at 0.1 and 0.1. So the width of the band reflects the lack of data, if you want. Okay. Here you have the same analysis, but flavor dependent, which shows you some hints of very different behavior of different flavors for what concerns the intrinsic transverse momentum. As you can see, again, at very low values of X, 10 to -3, you have big uncertainties, especially for the C quarks, which are very poorly constrained by actual data at very low X. And then the situation improves as you go to higher and higher X, where, for instance, the valence quarks, U quark and D quark, are very, very, very precisely measured, let's say. Okay, the uncertainty is very small. This is the Collins-Soper kernel I was telling you before. This is a comparison of many fits, also fits that I didn't mention before because they are not global fits. For instance, this BB19 is not a global fit, SB17 is not a global fit. But as you see, the comparison, I mean, they behave in a reasonably same way, except for the very large BT region, where the details of the fitting procedure, of course, matters. Very large BT region is the region that you are effectively fitting. Okay? It's very small QT. So here, if you want, the behavior is dictated by perturbative QCD because it's small BT, so large QT. So it is normal that here they look basically all the same. The discrepancies started in the very large BT region, and because in this region, the differences in the fit, the explicit fit count. This is another plot on the Collins-Soper kernel, quite different from the last one, because the last one was -1/-2K. This is directly K, so you just have to mirror with respect to the x-axis. And this contains, in addition to global and non-global fits, also predictions from lattice QCD. And so, as you can see, lattice QCD predictions are in decent agreement with these curves extracted by experimental data, also thanks to the fact that the lattice uncertainties are huge. Okay. So once lattice will become more precise, we will feel some pressure in reproducing lattice data. Okay. But for the moment, we can say we agree. All these groups agree with the lattice. Another item that you would easily find in a fitting exercise is the correlation matrix. This is not compulsory. You don't have to show correlation matrix for your extracted parameters, but it's useful to give this information because eventually you want to obtain, you would like to obtain a completely decorrelated matrix, so a fully diagonal matrix here. Because otherwise, that would mean if you have big correlations, for instance, like this one and this one, and also this one, it means that you have problems going on in your fitting procedure. Okay, maybe one parameter is too much correlated or anti-correlated to another, and you should carefully merge them or completely separate them or seek for alternative parameterization. Okay, this is a useful piece of information mainly because it drives yourself, it drives your personal choices in doing the fit. Okay. No, I will not comment on the parameter values. Sorry. Now, what can you do to see if you're doing a good job or not? You can perform all kinds of tests on your fit. Okay, the first test you can perform is to see who drives your X dependence. As I told you, Atlas and LHCb and CMS will mainly drive the X dependence because they have a wide range of rapidity and they are pinned in rapidity. So they will mainly drive your X dependence. How can you prove this? Well, you can try an X independent fit. For instance, this one, which was tried already in the 80s, with and without Atlas data, and see what happened. So if you try the X independent with the full data set of Atlas, you got these values of the global chi-squared. And if you don't include data, you get this value of the global chi-squared. This means that you get a chi-squared significantly higher for the full data set. And so X dependence is required to describe data. Okay? While you get a significantly lower chi-squared without Atlas data, which means that the X dependence at N3LL is entirely driven by the Atlas data. Okay? So by performing this test with and without the data, or with and without an X dependence parameterization, you can disentangle which experiment gives you information on what. Another test you can perform is the dependence on the QT cut. As I said, QT over Q has to be less than 0.2. But what happens if I choose QT over Q 0.175 or 0.225 or 0.275? It happens this. So your chi-squared rapidly decreases to 0.8 or rapidly increases to 1.4. And so maybe we are in a good region for QT over Q. Okay, so we could lower it a little bit, but it's more or less a stable region. We can safely conclude that QT over Q less than 0.2 is the good region for TMD factorization. Of course, you could do the same for a very complicated formula of series cuts. You can vary all these parameters here. C1, C2, C3. This is the one that I showed you before for the fits, but you can give almost random number for the other parameters, and you have this behavior of the chi-squared. So you can do better here, but it's a reasonable choice, also the one that we adopted as well. You can also test the convergence. You can perform a fit at next to log, next to next, or N3LL and see what happens. What happens is that if you improve your perturbative accuracy, data are definitely well reproduced. So this is the next to log, this is next to next, and this is next to next to next. So they approach, as you can see. So there is a nice convergence, which is also reflected in the chi-square that you obtain from the fit. Okay. Another test you can do is trying to use the results you have derived for your fit to predict what should happen at the LHC. So the impact on LHC data, for instance, in this version of the fit, we did not include CMS data, and we tried to reproduce CMS data with the results that we obtained from the global fit. And the results are encouraging, as you see, because the CMS data are reproduced. They are not fitted. I repeat, they are not fitted data, and so this is a prediction. And the same we have done for Atlas data. We have performed a fit without including Atlas data and a fit including Atlas data. And also in this case, the agreement is satisfactory, let's say. But there is an open problem. The open problem is semi-inclusive deep inelastic scattering. For Drellian, this is the plot I showed you before for the convergence of the perturbative series. This does not happen for series. For series, we have a big problem in the sense that at next to leading log, series data are quite well reproduced. See quite well with the exception of this one and this one, but I mean, we are on the same ballpark at least. But as soon as you go to next to leading log and next to leading log, the situation dramatically worsens. Okay, as you also can see from this ratio. This is almost a constant K factor that, as far as I know, no one is able to explain up to now. There is a normalization problem with series data. This is why we and other groups also resorted to a normalization of series data in order to compare with experimental data, because otherwise the comparison would not possible. Okay. So this is a problem that still have to be solved. It has been found maybe a possible solution to this problem, which are kinematic power corrections by Alexei Vladimirov in a very recent paper. Yeah, but I mean, it's really an open problem. We are not able to reproduce this data if not introducing this kind of corrections or a normalization computed a priori. So I already have finished my time, I guess, no? Because
You don't have anything in the evening, so take your time.
okay, thanks. Tell me.
So is plot on the bottom left just the ratio of the experimental data to whatever?
This is the ratio of experimental data to NLL,
Yeah.
and NLL, and then 3LL. So as you can see, NLL is reasonable. NLL stays on data, and then and 2LL and 3LL is completely off. This is also easy to understand. You remember there was a hard factor in front of the TMD formula, H series. H series is 1 at next to log plus alpha S H1. H1 for series turns out to be 30%, so 0.3. And so this is a lot, and it changes dramatically your normalization. And you need to come up with some solution to overcome this 0.3 factor in the H function. I will just give 10 minutes and I think I'll be finished. There is a delicate problem for the choice of scales. Okay? You have seen that the TMD formula depends on scales, which are the mu0, zeta 0, mu final, zeta final. So the initial and final scales for the mu and z scale. Normally, when you perform a theoretical calculation, you perform scale variation to estimate the size of the higher order that you're not including. And this is your theoretical uncertainty. Okay? But all the results that I've shown up to now do not include this information. They only include experimental uncertainties, statistical uncertainties, PDF uncertainties, but they don't include theoretical uncertainties because there is not a universal recipe, there is not an agreed upon recipe to do that. Okay? Why there are no formulas here? Sorry, this slide is... These slides are messed up. I don't know why, but okay. I will try to interpolate between the formulas which are not displayed. A sensible choice of scales is important to allow perturbation theory to be reliable, as you read, in the sense that you don't have to, you would not like to have large unresummed logarithms introduced in your formula, and you have to have scales as close as possible to natural scales. What are the natural scales? In TMD factorization, as Qt and Q are the natural scales. So a good choice for your input scales would be close to Qt, Q. Okay. Moreover, it turns out that in the MS bar scheme, also the bar is missing here, the central scales are these ones. The mu b scale that I guess Alexei already introduced in previous lectures, and the q scale at which you perform your evolution, both for mu and the final scale of rapidity. This is the choice that nullifies all the unresolved logs. So if you choose this mu b with this 2 times e to the minus gamma, you will not have spurious logs that are not resummed due to the MS bar scheme definition. Okay? Because when you're normalizing the MS bar scheme, you have this log of b, log of 4 pi plus log of gamma e going on. And so if you choose this scale, these logs will go away. Okay? So in principle, you should vary these 2 scales around mu b and around q. In principle, you should also vary the final scale of rapidity, but actually, you can also choose not to perform variation of zeta 1 and zeta 2 for your TMD PDF because they are linked anyway. That relation has to be exactly satisfied. Zeta 1 times zeta 2 must be equal to q to the 4th in the TMD formula. Okay, so any sensible, so here there was a slide showing that any sensible choice of zeta 1, zeta 2, which amounts to q to the 4th is reasonable. So you can choose q squared and q squared, or q squared over 2 and 2q squared. You can choose whatever you like, but since the evolution factor will only depend on the product, the zeta 1 and zeta 2, then this choice makes absolutely no uncertainty at all in your final result. Okay, so you can rely on a 2-scale variation as well. The problem with the 2-scale variation is then that you need an additional scale to parameterize the fact that you are stopping at some perturbative order. Okay? Mu0 parameterize in some sense the perturbative and non-perturbative physics because it's a scale at which you cut at which you start your evolution. Sorry. So it parameterize your perturbative and non-perturbative regions. Q is the hard scale of the process, which is related to, for instance, renormalization scale, because it's a scale at which you eventually will evaluate your alpha S. But then you need a third scale, because you need a scale to parameterize the fact that you're stopping, for instance, at N2LL. So you need a scale to parameterize what is the missing N3LL uncertainty. Okay? This usually in other approaches, in Qt resummation approaches, is called resummation scale. It is absent in the TMD factorization approach, and you have to find a way to mimic this resummation scale because it is eventually there because you're stopping your PDF, your fitting exercise at some perturbative definite order. A possible way of mimicking resummation scale variation is introducing N4LL corrections in the Sudakov exponent, so in the TMD formula, and see what is the impact of this introduction in your theoretical curves. The impact is this blue line here, light blue one here, much less than the so-called factorization scale or resummation scale in Qt resummation, and so reasonably well under control. But this is something that has to be exploited. I mean, we have to discuss a little bit on how to include theoretical uncertainties in TMD PDFs fitting because it's not it is not assessed in any ways. A few words about the future. What is the future? The future is providing results for the entire QT spectrum, as I said. So we cannot only rely on the data on the region we are expert in. We are expert in this region because we are doing TMDs. So we are expert in the region of very small QT up to 10 or 12 or 15 GeV for PTZ, for instance. But we want to make predictions also to large PT, for the large PT spectrum, where you have to consistently introduce a transition region where both your formalism and the fixed order perturbative result coexist. And so you have to find a proper matching for this collinear and TMD region. Another future prospect concerns the new experimental measurements that might be used to further improve our knowledge of TMD PDFs. This is the range of experiments available as a function of the lepton pair invariant mass from 1 GeV to 100 GeV and on. We are basically now in this region. CD's data, Drellian data that have been fitted are in this region, more or less. Low QT data in this region will be absolutely welcome because this is the region where TMD PDF might have a lot to say here. This region, I mean, could be relevant as well, but the problem is from the experimental side. Are we sure that QT nearly lambda QCT is attainable with decent precision by experiments in this region? I'm not sure of this, but maybe some experimentalists could comment. Of course, this is the region we must exclude because here you have resonances and the perturbation theory completely breaks. And here we only have fixed target data, very old with very big uncertainty. So also an improvement in this region would be very welcome. This is really for the future. You don't have only the PTZ that you can fit. You have many other observables which are sensitive to the TMD region, and this one is mainly the most interesting one is the phi star. Phi star is an angle which is derived from the final state lepton pair decaying from the Drellian. Okay, it is mapped onto small QT, and more or less the formula resembles like this one. So phi star is more or less QT over M. But since it is an angle, from an experimental point of view, is extremely clean. So they don't have to worry about lepton energy scales, reconstruction efficiencies. I mean, all these kind of problems that augment your experimental uncertainty, your experimental systematics are not there because they just have to measure an angle. And an angle is very easy from experimental point of view. And this reflects in the fact that these points are insanely precise. This is a 3 per mil uncertainty in the experiment. Okay, so since this observable directly relates to the QT, you can perform TMD predictions also for these observables if you dare. So if you dare comparing with this extremely precise uncertainty, then you can also extract TMD PDFs at an unprecedented level of precision. The problem is, are we really sure that we can obtain a 3 per mil precision in our theoretical predictions? Not for now and not for the near future. But this can be a really nice observable to consider. Let me skip this. Last one that I want to show you is this one. A very important side project of TMD PDF extraction is precision measurements. For instance, the W mass precision measurements. The W mass is extracted by its decay products, especially from the lepton PT of the W decay. This is the shape of the lepton PT. It has a Jacobian peak here, which is very much affected by soft radiation from initial state, and so it is very much the TMD region. So the TMD is very relevant in this region. When you vary the W mass and you produce templates with different value of the W mass, the shift in this profile is at the level of 10 to minus 4. Okay, you see? So if you aim to measure MW with a 10 MeV precision, which is what LHC is aiming to, then you need to control your perturbative predictions up to per mil level, as you see from this green line. Okay? And this is a region where TMD-PDF can say a lot. We tried, for instance, to estimate the impact of our flavor-dependent fit on this kind of observables, and we obtain a shift on MW consistent or comparable to PDF variations. So this is an item where TMD PDFs can say a lot and can produce a lot of interesting results. But there are also many, many others. So the Higgs PT can gain a lot from TMD PDFs, and all kind of precision measurements would rely on a TM-PDF setting. So with this, I apologize for being so so long. I think 20 minutes more. And so I thank you for your attention. I ask for questions if you have. Yeah.
Can you just explain your MS bar scheme scale?
You're right. Maybe I can, because the formula were missing but there are a few missing formula in there that will explain a lot. So if I can show you maybe during the break, I will show you my slide with full formulas and you will understand. It's basically because of the fact that with the MS bar, you have the appearance of several terms which have a kinematical origin and are not resummed. And with that choice of scale, you can eliminate this kind of. But I will show you because it's much more easy than with words.
Report only the term which is related to the comparison with data shifted theory, or also the penalty term.
All the plots you have seen are produced with shifted prediction.
Yeah. No, that I know. But then you report the chi-square and you say how good your fit is. What do you use?
We put several columns: the chi-squared penalty, and the chi-squared. So you have. I think that what I put on slides was the total. But then you can gain some information. That's a good question. You can gain very useful information from the size of the penalty term. If the penalty term is too much, then you have problems. Yeah.
Can you go to your prediction for CMS? Yeah. Not just here go. So what's happening there at Q square less than 100 but greater than 50? QT.
What's happening where?
QT greater than 50, less than 100.
Here.
Yes.
I mean, here, TMD factorization. You wouldn't expect TMD factorization to work above 20 or 30 or 40 GeV. Here
So that is not. You have no matching.
No.
This is pure prediction.
This is pure TMD. This is pure TMD, and then you have to match with the fixed order perturbation. We didn't.
Don't have any negative cross section.
No. Now, the next frontier would be actually to explore the transition region, because transition region can be used also to gain information on the rhythm structure. And the urgent thing to do is to understand why CDS is not reproduced.
For a build, I see. All right. Any other questions or comments? Everybody wants to go to lunch. Let's thank everyone.
And just a few notes, so the